Welcome back. So in this video, we will formally describe the central limit theorem, which is one of the foundational theorems of classical statistics, and look at some examples of how well the central limit theorem works in practice. So the central limit theorem really comes down to this idea of the behavior of the sample mean. How is it distributed? What's the shape of its distribution? We already know how to find the expected value in variance of a sample mean, but how can we really go beyond that? So a sampling distribution refers to the distribution of a sample statistic. So anytime we take a sample of data, calculate some statistic like the mean, the sample proportion, the minimum, and the median are also very common statistics. How are they distributed? What would we expect to get for those? Now, when the number of observations in our sample is sufficiently large, we have a very nice and convenient result for the mean in particular. And that result is the central limit theorem. So formally speaking, let's let y1 through yn be an independent and identically distributed sequence of random variables with finite mean mu and finite variance sigma squared. So we will take a look, or we'll consider the sample mean y bar. The distribution of the standardized sample mean converges to a standard normal random variable. So in other words, if we take our sample mean y bar, calculate the difference between the sample mean and the true population mean mu, divide by sigma over the square root of n, that converges to following a normal distribution. So that z-score is distributed normally with mean 0, standard deviation 1 as the sample size increases. So what do we need for this result to kick in? Well, we need to have a finite mean and variance, so finite mu, finite sigma squared. We also need to know what they are, which in practice is a pretty dubious assumption. But for now, we'll assume that the population mean and standard deviation, or mean and variance, if you will, are in fact known. Here is what's not present anywhere in that central limit theorem statement. So far, we have been assuming that the population itself is normally distributed, but it turns out that that's not actually a condition of the central limit theorem whatsoever. So we don't actually need to have that normal distribution as long as we have a sufficient sample size. So eventually, the sampling distribution will converge on the standard normal shape, assuming our sample is large enough. So let's take a look at an example. Customers at a popular restaurant are waiting to be served. We'll assume that the waiting times are independent and exponentially distributed with mean 30 minutes. If 16 customers are waiting, what's the probability that their average wait time is less than 25 minutes? So we will assume that n equals 60 is large enough to use the central limit theorem, which would mean that the sample mean is normally distributed. The mean mu is the population mean. The variance of the sample mean is the population variance, over the sample size n. So then the probability of observing a sample mean less than 25 according to this distribution is about 25%, 0.2525. Now, how close is this central limit theorem result to the actual probability? So we know how the sum of exponentials is distributed mathematically. That follows a gamma distribution. If I can take a look at how the sum of these exponentials, or how this gamma compares to the sample mean, which is just the sum over the sample size, then I can get an idea of how closely the central limit theorem matches the reality. So let's let u be the sum of these exponential distributions. We know that follows a gamma. So then the probability that the sample mean is less than 25 is the same as the probability that the sum of the wait times is less than 16 times 25, or that the sum total weight is less than or equal to 400. Using a gamma distribution, that's 0.2666. So even for a small sample, which 16 is fairly small in practice, the central limit theorem is only off by about 0.01. We had a previous probability using the central limit theorem of about 25%. Here we have a probability of about 26%. So the answers are pretty close using these two methods. Now, most often, we won't be in a situation where we can clearly find the distribution of the sample mean. It might not follow one of the named distributions. So that central limit theorem gives us a good approximation to the true sampling distribution, or to the true distribution of the sample mean. So let's take a look at this result to the sample mean. Let's see, well, how closely this follows. So we know again that the sum of exponentials follows a gamma distribution, but we don't know how the mean of exponentials is distributed. So what I'm going to use is a simulation to get a picture of what this mean looks like. So I'm going to take 10,000 samples. I'm going to calculate each of these sample means by creating a sample of simulated data, calculate the means for each row. So this is a very concise program here to do this. I'm going to add up how often that sample mean was less than 25, divide by my number of simulations. So that's going to give me an estimate of the probability. Estimated probability of getting a sample mean less than 25 minutes is about 26%. More importantly, here's what this distribution of sample means looks like. It's still mimicking the exponential distribution, and then there is some right skew. But if we look at where the bulk of this distribution lies, it has that familiar bell shape starting to peek through. It's starting to look normal. Again, these samples only have 16 customers or 16 observations. These are very small samples. The larger our samples get, the more observations we have, the closer this will get to a normal distribution. So let's take a look at another example. So this example takes a look at data from the AP Statistics exam in 2017. Over 2.7 million students took at least one AP exam. AP Statistics that year had roughly 400,000 takers. So here's the grade distribution. The AP exams are graded on a score from 1 to 5. Typically, college credit in the subject is awarded for a score of 4 or higher. So that's what most students are aiming to get in order to get college credit. So on the AP exam, for statistics, about 14% of students got a 5, which is the highest score. About 16% got a 4, about 0.245 got a 3, and so on. What's the probability that the average score is above 3? So this is an example of a discrete distribution, and certainly scores on the AP exam don't really follow one of our named distributions. But we can find the expected value of a score on the AP exam. We can find the average score. We can find the variance. That should be all we need to work with the central limit theorem. So our expected value is found by taking the realized values, so the scores, times their corresponding probability. So we get an expected value for the AP exam score of 2.7. Variance found by taking the expected value of y squared minus the expected value of y quantity squared. We get a variance of 1.848. So by the central limit theorem, if we take a sample of 100 students, that sample mean y bar will follow a normal distribution with mean equal to the expected value, so 2.741, variance of 1.848 over 100. So our probability that our sample of 100 students will have a mean score in the AP Statistics exam greater than 3 is only about 2%. It's a fairly unlikely event. So using a weighted sampling function in R, I actually went ahead and generated 1,000 random samples of 100 AP Statistics scores. So this is a picture of what the sampling distribution should look like. Takeaway here. This looks a lot like a normal distribution. So even with discrete distributions, if the sample size is large enough, the central limit theorem tends to kick in. Now let's take a look at some other examples. So we have a bottling machine that is regulated so that it discharges an average amount of mu ounces per bottle. We've observed that the amount of fill dispensed by the machine is normally distributed with sigma equal 1 ounce. We're going to take a random sample here of 9 bottles that are randomly selected from the output on a given day. Here's what we'd like to know. We'd like to find the probability that our sample mean will be within 0.1 ounces of the true mean for the chosen machine. So I'm going to let y be the amount that's dispensed by the machine. Since y itself is normally distributed, we don't actually need the central limit theorem to tell us that the sample mean will be normal. The average of normal random variables is in fact normal. So this is how our sample mean is distributed. It's distributed with mean mu, variance 1/9. Now, without loss of generality, let's place that mean mu somewhere, say at 20. So then the probability that we're looking for, that the difference between the sample mean y bar and the population mean mu is 0.1 ounces, can be found like this. It's the probability that mu minus 0.1 is less than the sample mean, which is less than mu plus 0.1. We'll just throw 20 in because we need to throw in a value for the mean in order to calculate this. So we get about a 24% probability of being within this range. Now, let's say we're going to take a higher sample. We're going to take more observations because clearly we're not often going to be very close to the population mean mu. How many observations are we going to need to take to get to that point? So we'd like to find the value of n so that this probability is 95%. We could start by just trying a few. So we tried 10 originally. We tried 9 originally. If we bump that up to 10, that doesn't get us very far. If we go up to 20, 30, we're still not really reaching a high enough sample where we're concentrating or narrowing that sampling distribution down enough. So let's keep going. Here, you can see that I've calculated sample sizes all the way up to 500 and this bound. The first sample size that crossed that 95% threshold for me was 385. So if our sample, or if our population, has a relatively high variance, then it's going to take a while. It's going to take a lot of information or a lot of samples for that range to really narrow down. So in the next video, which is the final one in this Math Stats 1 series, we'll take a look at some constructed distributions, so some other distributions that can be useful to describe samples. See you then.